Hi guys, and welcome to another HSC Chemistry video in the acidic environment series. Last video we looked at reversible reactions, and we want to look at them again from a slightly different perspective as we investigate Le Chatelier's principle. Now, the important thing about equilibrium systems is that we have looked at them before, and there are a couple of important things we just need to be aware of. First of all, they must be closed systems. If the system is open, it can never reach equilibrium, so it must occur in some sort of sealed container. There must be no macro level changes occurring, so we can't see any changes of the color, we can't see any other obvious signs, temperature rises, gas bubbling, those sorts of things that suggest that the reaction is still proceeding, but we've actually reached a point where it looks like there are no more changes occurring. And at least at the macro level, we can't see any more change that's actually occurring. And at this point, it's the rate of the forward reaction that's equal to the rate of the reverse reaction. Always important to remember, equilibrium is about rate of reaction, not about the amount of the different substances. So the position of equilibrium is what actually relates to the amount of the different substances. So one of the things that we use to describe whether or not the equilibrium is in the middle, if you like, or whether it lies to the right or the left, is to compare the amount of each of the substances at the equilibrium position. What we do when we realize that is if we have a lot of reactant and little product, so for the reaction down the bottom, the dinitrogen tetroxide in this case would be the reactant, and the nitrogen dioxide would be the product. So in the first case, if we have lots of N2O4 and little of the NO2, then the equilibrium lies to the left. That is, we have a lot of the reactant. If there is little reactant and a lot of the product, so in the one down the bottom, that means we have a lot of NO2, and therefore the equilibrium lies to the right. So the rates of reactions are equal, but at that point where the rates of the reactions are equal, there is more product than there is reactant for an equilibrium which lies to the right. Now, once equilibrium has been established, it can actually be changed or moved, and it's moved according to Le Chatelier's principle. Now, there's no simple way really of remembering this, so have a look at the definition and then see if you can get an idea in your head about how you might use this to explain what happens in equilibrium systems. So first of all, the system must be in equilibrium. And when that equilibrium system is subjected to a change, so the key word in Le Chatelier's principle is change. We need to change something about the system, either the concentration of one or more of the substances, the temperature of the reaction chamber, the external pressure is particularly relevant when we're talking about one or more species that are in the gas phase, or some other factor which upsets the equilibrium. The system reacts in such a way as to counter the change. So what we do to the system will try and reverse. If we increase the pressure, it will shift to try and decrease the pressure. If we increase the temperature, it will shift to try and decrease the temperature. If we remove some of the product, we decrease the concentration of that product, the system will shift in order to try and replace that lost product and increase the concentration. That's the application of Le Chatelier's principle. So here's an equilibrium system for you. I gave you a little bit of a look at it on one of the previous slides. In this slide, we have dinitrogen tetroxide, which is colorless, shifting to nitrogen dioxide, which is brown. At a macro level, there will be a color change. If we start with dinitrogen tetroxide, which is brown, it will fade, that color will fade as the N2O4 is formed because it's colorless, and therefore some of that brown color will fade until it stabilizes. The color doesn't change anymore. Likewise, if we start with N2O4, it will establish an equilibrium with NO2 by producing that particular molecule, and we will start to see the brown color appearing. until once again there is a stabilization. Once that stabilization occurs, so color stable, that is an indication that we have reached equilibrium. For the forward reaction, the delta H value is positive. So this tells us it is an endothermic reaction. If we were to remove NO2 from this system, then that would mean the concentration of NO2 would drop. The system would then shift to produce more counter change equals shift to the right. That is, the equilibrium will shift this way in order to produce more of the nitrogen dioxide which has been removed. If we increase the pressure, we have molecules bouncing together much more closely. That's what increased pressure is. So in order to counter, what we do is we shift to the left. So every 2 moles or 2 molecules of nitrogen dioxide will produce 1 mole or molecule of the dinitrogen tetroxide. So increasing the pressure favors less gas moles. And finally, if we were to increase the temperature, we favor the counter is endothermic. So therefore, this will be a shift to the right. In the forward direction, it is endothermic. We take in heat, so that extra temperature, that extra heat can be taken in through the formation of NO2. This has been a longer video because there's a lot of, I guess, consequences of the application of Le Chatelier's principle, and definitely something you should have a go at as part of your study practice. Thanks for watching.